In our previous section, we looked at measures of central tendency, so we're measuring where the data tends to gather. In this section, we're going to be looking at what we call measures of dispersion. And when we talk about dispersion, how things are dispersed, it looks at how the data is spread. Okay, and there's going to be two types. The first is the range, and that's very easy. The second one is what we call the standard deviation. The range just looks at the highest data value and we subtract the lowest data value, so it's the difference between the highest and the lowest. In example 1, if we were to find the range for the following test scores, so for A, the lowest test score is 64, the highest test score is 72. So when we compute the range, it's just the highest, 72, minus the lowest, which is 64. So that would give us 8. Super simple. Part B, the lowest is 40, the highest is 100. So my range is just 100. We'll subtract 40 to get 60. The next measure of dispersion is the one that we used most often, and it's called the standard deviation. Now, the standard deviation, very loosely speaking, it just measures the average distance of the data items from the mean. So it looks at how your data items are spread from the mean. First of all, to compute the standard deviation, we're going to talk about what a deviation is. So when we look at a deviation, it's just our data item and we subtract the mean. In example 2, we're going to find the deviations from the mean for the following data items. So that would be 40, 70, 70, and 100. So since we have to take our data items, which we have, and we have to subtract the mean, I need to find the mean, which I don't have. The first thing I need to do to find the deviation is compute the mean. So remember, the mean is add everything up. So it'd be the 40 plus 70 plus 100, and divide by how many you have. We have 4. This should be 280 over 4. And our mean is 70. Now that I have the mean, I can compute the standard deviation. So the standard deviation is a subtraction, which means the order matters. The data item has to come first. So for the data item of 40, the deviation is 40 minus the mean of 70, and this deviation is going to be a negative 30. So the deviations can be negative, they can be positive, they can also be 0. For 70, when I subtract the mean of 70, I get a deviation of 0. So remember what I was saying. We're looking at a deviation from the mean, kind of like a distance from the mean. Well, if the deviation is 0, that means our data item is the mean, which is true in this case. So I have the other 70. I don't really have to do this one because I've already done it in a previous step. But then the last one would be the data item of 100 minus the mean of 70 gives me a positive 30. So whenever you have a set of data items and you take data item minus mean to find the deviation for each data item, then the total, if I were to total up all these deviations, will be 0. And that's why I listed the data item 70 twice, because it showed up twice. So the sum of the deviations will always be 0, and that would be unless you are looking at decimal approximations for your deviations, but we didn't round any of our deviations. Now that we know what a deviation is, we can compute the standard deviation. Here's a formula. The first step is you need the mean, and then you need to find the deviation. So we already did that in our previous example. The third step is that you're going to take each one of those deviation and you're going to square them. So what that does is if the deviation is negative, it'll turn positive. So you're going to take the data item minus the mean, that's your deviation, and then you're going to square the whole thing. After you square each deviation, you're going to sum them or add them all up. So that's where we're using this sigma notation. That means to sum or to add. So that says that you're going to add all those deviations squared. The fifth step is you're going to take that sum and you're going to divide by n minus 1. N is the number of data items. So you're going to take 1 away. So this is our formula so far. Sum each deviation squared, divide by n minus 1, which is the number of data items minus 1. Our last step is to take the square root of all of that. Now, if you have a fancy calculator, or there's a lot of scientific calculators online, then you can do all of this in one step. But if not, you're going to have to do it in steps. We're going to go ahead and practice taking the standard deviation, and I have all the steps listed here. You don't have to do it this way. And in fact, I probably won't list all the steps after a while. I'll just do them. Example 3, we want to find the standard deviation for the data items we had before, 40, 70, 70, and 100. So remember the first step was to find the mean, and we already did that in our previous example. We found that the mean was equal to 70. Step 2 is to find the deviation for each one, and we did that for each data item. Even if it repeats, you still have to write it down. So we already did that previously. Remember, 40 minus 70 gave us the negative 30, and then we had the 70 minus 70, which was 0. 70 minus 70 is 0. And then we had the last data item of 100 minus the mean of 70 gave us a positive 30. So once we square each one of those, we're squaring negative 30. So that should be a positive 900. And then we're squaring 0, which is simply 0. Square 0, it's 0. The last one would square a positive 30, and that's a positive 900. So those are all our deviations squared. The next step is to add those up. So 900 plus 900, that total is going to be 1800. So we're going to divide by n minus 1. We have 4 data items. So in this case, n is equal to 4, which means n minus 1 is equal to 3. We take our 1800 and we divide it by 3. Now this particular example, this turned out to be something nice. It turned out to be 600. But oftentimes when you divide by your n minus 1, you'll have this really long decimal. My advice is don't round. Write whatever's on your calculator down, unless you're doing all of this in one step. The last step is to take the square root of what we had in our previous step, which was the sum of the deviations squared divided by n minus 1. So this is the square root of 600. Typically, we'll put it in our calculator and get a decimal representation. Why don't we just go ahead and round it to 1 decimal place? Oh, round it to 2 decimal places, because that's what it says in the instructions. So if you take the square root of 600, then you get 24.494. So it should be 49. And that's how you find your standard deviation. You just follow all those steps. Example 4, we're going to find the standard deviation for 2 sets of data items. We have sample A and we have sample B. So this will give us a lot of practice. And then we're going to round our standard deviation, and this is the final answer. We're going to round to 2 decimal places. Then sample A, the data items that I have are 73, 75, 77, 79, 81, and 83. Now remember I said the standard deviation, loosely speaking, is sort of like a distance from the mean. Notice that all these data items in sample A, they're really close together. If we were just to look at the range, it's 10. So since these data items are very close together, that means the standard deviation is probably going to be really small, because the distance from the mean, which we still have to compute, is they're going to be very close to the mean. So first of all, I need to find the mean so that I can find my standard my deviations. So our mean would be equal to add all of these up, the 73 plus the 75 plus the 77 plus 79 plus 81 plus 83, and then divide by 6. When I do that, I get 78 for my mean. Now I can find the deviation for each one of these data items. So the first one would be 73 minus the mean of 78. This is going to give me a negative 5. 75 minus 78, negative 3. 77 minus 78 will give me negative 1. 79 minus 78 is positive 1. 81 minus 78 is a positive 3. And then 83 minus 78 would be a positive 5. Notice if I were to add up these deviations, it is 0, so I did my math correctly. The next thing is to square each one, so the negative 5 squared becomes a positive 25. The negative 3 squared becomes a positive 9. Negative 1 squared becomes positive 1. 1 squared is positive 1. 3 squared, positive 9. And then 5 squared would be a positive 25. The next step would be to add up these squared deviations. And when I do add this up, I get 10, 20, 40, 60, looks like 70. Nice number, so I could do that in my head. So notice that n minus 1, we have 2, 4, 6 items. So 6 minus 1 is 5. So I'm going to take that 70, I'm going to divide it by n minus 1, which is 5. So I can do that now and I'll get a nice number. But I'm going to put this all in my calculator in one shot. I'm going to do the square root of 70 divided by 5. And now in the instructions, it said to round to 2 decimal places. In my calculator, I have 3.74165, so 3.74, which seems about right because the data items are really close together. So that's it. Find your mean, find the deviation for every data item, even those that repeat, square each one, total them, divide by the n minus 1, take the square root. Let's do another example. We'll look at sample B. So the data items are 40, 44, 92, 94, 98, and 100. Just by looking at B, I noticed that those items are spread out a little bit more. Look at the range there. The smallest is 40, the largest is 100, so the range is like 60. They're really spread out. So I'm thinking the standard deviation would be a little bit larger as well. Remember, that's a distance from the mean. Let's go ahead and find our mean. So remember, when we find the mean, it's going to be 40 plus 44 plus, and then we jump to 92 plus 94 plus 98 plus 100. oops, divide by 6. I'm going to stick that in my calculator, and I get 78. So it's the same mean as the previous sample, but in this case, the data items are spread further apart. So the means could be the same. That's why we talk about using different types of measurements to get a better picture of our data, because both of these data items, sets of data items, have the same mean, but in sample A, they're all kind of clustered together. In sample B, they're more spread out. So the standard deviation should be higher in this case. Let's go ahead and list all our data items. We had 40, 44, 92, 94, 98, and 100. And then we'll find the deviation. 40 minus 78, that's going to be a negative 38. 44 minus 78 is going to be a negative 34. 92 minus 78, that's going to be a positive 14. 94 minus 78, positive 16. 98 minus 78 is a positive 20. And then 100 minus 78 would be a positive 22. At this point, I'm going to take each one of these deviations, the negative 38, and I'm going to square this to get 1,444. Then the negative 34 squared would be 1156. 14 squared, 196. 16 squared, 256. 20 squared, 400. And then 22 squared, 484. Squared each deviation. My calculator, I'm going to total this all up. And I think this is 3936. My n minus 1 is still 6 data items minus 1, still 5. So I'm going to take 3,936 divided by 5. Then I'm going to take the square root as the last step. So again, I'm just going to put this into my calculator. And when I do, I get 28.06 if I were to round to 2 decimal places. So notice this standard deviation is what I expected it to be. It's a lot higher because my data items are more spread apart. So again, if your data items are closer together, your standard deviation should be lower. If they're spread apart, your standard deviation should be higher. And that's the whole point of this section, is to measure how far apart our data items are. Okay, so that's it for this section 12.3. And then in 12.4, we'll move on to go beyond measuring our data items. We'll go ahead and look at how we can get some information from how our data items are spread out. In particular, we'll be looking at normal distributions.